All right, everyone, welcome. Today, we're diving into something that is, well, the absolute foundation of all physics. We're talking about units and measurement. Think of it as the language we use to understand, well, everything, from the tiniest particles to the most massive galaxies. So, you ready? Let's get right into it. Okay, so let me ask you something. What if I told you that a table was, say, 5 feet long, and then you went and measured it with your own feet? Would we get the same number? No way, right? My foot is definitely not the same size as your foot. And this simple little problem, believe it or not, was the source of so much confusion for centuries. We needed a standard. So how do we fix this whole my foot, your foot problem? Simple. We use something called a unit. A unit is basically just a deal. It's everyone in the world agreeing, okay, this specific length is what we will all call 1 meter. It becomes a universal reference point, so my meter is your meter, whether you're in one country or another. It's our common language for measurement. Okay, so let's dig into why we needed these standard units so badly. We're going to see just how messy and confusing things were back in the old days. So, check this out. It was a total mess. You had some people using the CGS system, that's centimeter, gram, second. Then you had the British system, FPS, foot, pound, second, and others were on the MKS system, meter, kilogram, second. Just imagine being a scientist trying to share your work with someone from another country. It was a recipe for disaster. Constant mistakes, total miscommunication, a real nightmare. And out of all of that chaos came our hero, the SI system. It's basically the world's official, agreed-upon measuring tape. So this system, the SI system, is the one everyone finally agreed on back in 1971. It's the standard for pretty much everything now. Science, technology, business, you name it. It just made life so much simpler. No more trying to convert feet to meters or pounds to kilograms. Everyone was finally on the same page, speaking the same language. Now, this is really important. The entire SI system is built on just 7 base units. Think of them like the letters of the alphabet for physics. You've got the meter for length, the kilogram for mass, the second for time, and so on. Everything else we measure, speed, force, energy, all of it, is just a combination of these 7 basic building blocks. Pretty cool, right? All right, so we've got our standard units, we're all speaking the same language. But just knowing the language isn't enough. You have to be precise. And that's where our next big topic comes in, significant figures. This is all about being accurate and honest in our measurements. So what on earth are significant figures, or sig figs as we usually call them? Well, they're basically a way of showing off how good your measurement really is. They include all the numbers you're absolutely sure about, plus the very first number you had to kind of guess or estimate. It's like being honest and saying, hey, my ruler isn't perfect, and this is the most precise I could be. Now don't worry, there are some really simple rules for counting them. Rule 1, any number that isn't 0, it's significant. That's the easy one. Rule 2, zeros that are sandwiched between non-zero numbers, like the 0 in 2.308, that 0 counts. It's significant. Rule 3, zeros at the very beginning of a number, like in 0.002308, you can ignore them. They're just placeholders, not significant. And finally, Rule 4, the tricky one, zeros at the end of a number are significant, but only if you see a decimal point anywhere in that number. So in 3.500, those 2 zeros at the end, they are absolutely significant. Okay, quick pop quiz. How many significant figures in 287.5 centimeters? Let's use our rules. All of these digits are non-zero, right? So all 4 of them count. The answer is 4. See? Not so bad at all. So what happens when you do math with these numbers? When you're multiplying or dividing, you've got to follow the weakest link rule. It's simple. Your final answer can't be more precise than your least precise measurement. So you just find the number that has the fewest significant figures, and that's how many sig figs your answer should have. Let's look at an example. Say we're calculating density. Our mass here is 4.237 grams, that's 4 sig figs, but our volume is 2.51 cubic centimeters, that's only 3 sig figs. So who's the weakest link? The volume, right? It only has 3. That means our final answer for density can only have 3 significant figures, so we have to round it to 1.69. You can't just write down all the numbers your calculator spits out. Now for adding and subtracting, the rule is a little different, so pay close attention. We're not looking at the total number of sig figs anymore. This time, we're looking at the number of decimal places. The weakest link is the number with the fewest places after the decimal point. Your final answer has to match that.
All right, on to our final concept for today. And this one is like a secret superpower for physicists. It's a super cool trick you can use to check your own work and see if your equations even make sense. It's called dimensional analysis.
The main idea behind this is something called the principle of homogeneity. Now, that sounds fancy, but it's really, really simple. All it means is that you can only add and subtract things that are the same. You can add apples to other apples, of course, but can you add apples to oranges? No. Well, physics is exactly the same. You can only add a length to another length or a mass to another mass.
I mean, it's just common sense when you think about it. You can't add velocity to force. They're not the same kind of thing. They have completely different dimensions. One tells you how fast something is moving. The other tells you about a push or a pull. They just don't mix. Let's test this out on a really famous equation. Here, x is position, which is a length, so its dimension is L. Okay, the next part, x naught. That's also a position, so that's L too. So far, so good. Now, v naught times t, well, velocity is length over time, and we multiply by time, so the times cancel out, and we're left with L again. And the last part, acceleration is length over time squared, and we multiply by time squared, so again, the times cancel out. And what are we left with? L! Look at that. Every single piece of this equation has the dimension of length. That means the equation is dimensionally correct. It passed the check. But, and this is a really big but, here's something to think about. Just because an equation is dimensionally correct doesn't automatically mean it's physically correct. For example, in that last equation, what if the number was 1/3 instead of 1/2? Or if there was no number there at all? The dimensions would still check out perfectly, but the formula would be totally wrong. So this superpower is a fantastic check, but it's not foolproof. Why do you think that is? What are its limits? I'll leave you with that question to chew